welcome to our webinar series in a very interesting topic by our colleague from ETS Montreal, who will be talking to us about aerial and IRS-assisted edge computing for intelligent transportation services. And the structure of the webinar will be, he will be covering this topic for the next 50 minutes, and then the floor will be open for your questions. Dr. Jaafar, Wael Jaafar, thank you again for accepting to be one of our speakers for this series, and welcome to the webinar. The floor is yours.
Thank you very much, Dr. Musa, and thank you everyone for attending today's presentation. So this work is entitled Aerial and RIS-assisted Edge Computing for Intelligent Transportation Services. So my name is Wael Jaafar. I'm professor in Department of Software and IT Engineering within ETS Montreal, and also I'm secondary affiliated to Department of Aerospace. So this is a new department, Aerospace Engineering in ETS. So actually I will go through maybe rapidly through presentation about ETS and what we do. So ETS is founded in 1974. It has more than 11,000 students that have enrolled here. It trains 25% of all Quebec engineers. So it's like the first in Quebec. And we do a lot of research with industry. About 70% is done with industry. Since it's not the big university, it's just engineering faculty, so it has a global ranking. You can see this in Scholar GPS, which is 181 worldwide. So because actually it has very, very intense activities in terms of research. So about myself rapidly, I'm associate professor since 3 years ago. Before that, I did research as a postdoctoral fellow in Carleton University in Ontario. Also, I worked also in the industry for almost 4 years, and I graduated from Polytechnique Montreal before that. For my current research interests, so what we do is that we have very high interest on non-terrestrial networks, so either supported by drones, HAPS, satellites. So we had a lot of work at first involving drones, either what we call tethered or not tethered or untethered drones. And also we worked a lot on HAPS. And one of the ideas also, what we see here is that we use HAPS to support intelligent transportation services. And finally, we looked into, of course, edge computing, federated learning, and cybersecurity in non-terrestrial networks. So this aspect also is very focused, and it involves a lot of work, specifically, let's say, in the cybersecurity, which is a new direction that we started work on maybe 1-2 years ago. So to go back to the main topic, I start with the general introduction. So we know that we have highways, we have routes that change the way of our lives. We have more traveling, we have goods moving between countries, continents, cities, etc. And this acceleration of globalization had made, so actually it stimulated the development of markets, the development of trade between countries and continents. So here in this picture, I'm just showing to you examples of important goods lines in different countries. So for example, in Canada, we have this Highway 1 that crosses Canada from east to west. So this is, I think, about 6,000 kilometers or more. And then, for example, Australia has a loop highway that goes around it. And in Africa, for example, there are many, let's say, intercontinent highways that goes either like in the coast or actually going through countries within the continent. So there is this huge development for transportation traffic. And of course, with this rapid globalization and inter-border supply chain networks, we have to make sure that we have reliable and efficient transportation systems. So this becomes more and more critical. And just to give you an idea here, we have shipping freights that would account for transportation over 90% of goods around the world. And then you have a cost for transportation. So I have some old information. So for example, it went from $1,300 in 2019 to above 9,000 in 2022. So actually, this is just after COVID. So actually, you can imagine now this cost is even higher. So, and we have very expensive routes. For example, in Asia and North American East Coast, these transportation costs can be very high. In parallel to that, so we have this development of highway infrastructure that is also driven by technology. So now we have this new intelligent transportation systems that would rely on vehicle to vehicle or vehicle to infrastructure or vehicle, what we call vehicle to X communication. And this integration with this new technologies for communication is also relevant either in these types of intercontinental highways, but also that is relevant in densely populated mega cities, where actually the road infrastructure can be under stress due to this high urbanization. And of course, we have this problem of road transportation accounts for about the third, maybe now it's about the third in global CO2 emissions. So the use of these ITS tool is really important, and it has to be looking to optimize traffic, road infrastructure management, and of course, we want to reduce the carbon footprint. So to give you an idea about how these things have been developing. So at first, we have this intelligent transportation system that have been looking into people, vehicles, and roads. So how this all converge together through technology. So now we have sensors, IoTs, radar, data processing that can be even on board, transmission of information in real time, and intelligent control. And usually the objectives that we were looking at with these ITS is safety, mobility, productivity, and comfort. So these are the four objectives that usually we want to achieve. But of course, we cannot achieve them all at once. For example, when you are in urban areas, you have one advantage. The advantage is that you might have cellular infrastructure, which allows you the V2X communication. And in this case, you have cellular base stations, you have roadside units that are there, and they are very helpful. And in urban areas, the most important thing is productivity. So we want to be productive. We want our trucks, when they go from point A to point B, to be as fast and eco-friendly, so actually consuming less gas, etc. In our case, if it's electrical car, of course, we wanted to take the shortest road in order to save this energy for next trip. So productivity is the main thing. But if you go outside these big centers and then you go outside on highways, it changes, because now it's not about productivity, it's mainly about safety. Of course, the other ones are still there, but safety becomes first. Why? Because in highways, cars run very fast, and then any alteration, any change in the highway can be problematic and can cause like jeopardize the whole trip, for example. So this is the difference, let's say, between these two. So in transcontinental highways, to be specific, we have other problems. So this cellular network that we mentioned here is not there, because many segments of the highways would be not covered by any network. And you might be think of mountain areas, of areas between cities. I mean, for the fun, for example, going from Montreal to Ottawa, in your trip, at some point you will use all cellular connectivity. And it's funny, like how come that you're traveling from one city to another, and in the middle there is no coverage, that we have coverage holes. So it's really a big problem, and such problems cannot allow a sustainable ITS or intelligent services, transportation services. And of course, why it's like that? Simply because between Montreal and Ottawa, there is no one living there. Or at least if there is someone living there, the number is so small that it's not revenue generating for operators. So they won't deploy infrastructure there. That's one part about this connectivity problem. The other thing is about the development of ITS. So ITS, and you look, I hope you are able to see here, it has big development has been pushed through the automation of driving, so autonomous driving. And this has been developing a lot. So you know that you have different levels in autonomous driving. You have level 0, 1, meaning that you need a driver, a human driver, to drive the car, because actually you don't have many sensors there. You don't have many information. You might have, for example, some radar, some sensors that will tell you, oh, when you're getting close to a car, then you have to brake, or it tells you, it starts beeping, etc. So you don't have much information coming in, but the human is still there. Level 2, you have partial automation, meaning that you still need a driver, but you have some automation. For example, the automation will tell you when you are on a road, on a highway, to stay on your lane. So don't make, it won't let you make a steering to right or left if you did not, for example, put your flashlights saying you will change the lane, for example. Or actually, if the sensors see, or the cameras see cars next to you in your dead angle, it won't let you do it again. So it's partial automation. And then you have level 3, which is conditional automation, which is eyes off, meaning that driver is not always mandatory for driving. And this is actually, level 3 is the first step of autonomous driving. So for example, we have cars in clear weather. It will drive itself on a highway. Very simple. So it will make sure that it drives on the lane. It can maybe it brakes or accelerates depending on the traffic by itself. So the human driver will not be required all the time. And then level 4 is that you don't have to let's say to be focusing that much. So driving would be functional under certain conditions. For example, if there is traffic jam or not, if the weather is clear or not, etc. So this can be considered. And level 5, of course, is full automation, where actually you are no longer a driver, you're just a passenger in the car, and the car drives itself. So we are not here yet. So we have a few steps, maybe a few things have been done, level 3 and 4, but not to level 5. And this all, if you see here a little bit, the number of sensors and cameras and what we need as information, it's just start increasing. So it goes from 6 to 28. Of course, 28, this is maybe an average number. Maybe we need more or less, depending on what we do. But what is interesting about these levels of autonomous driving is that it generates traffic, a lot of traffic. And this can be considered, actually, if you look here, you can see that you might be generating, for example, for level 1, between 160 and 320 megabits per second. I mean, if we specifically, if you consider you have a camera, you have radars, etc. So, and this just keeps going up. So there is a lot of data that has to be processed. And if you want to get full automation, you have almost 4 or 5 gigabits per second data you have to process in real time. So which is huge. Of course, there are techniques to simplify this, to approximate, etc. But just to give you an idea about how much data is there. So in this case, if I have some processing power in the car, and I have to process all this, so actually it might not be enough, or for some reason this power is not fully used. And in this case, you have to offload some of this traffic to be processed elsewhere. And this is where actually we've been looking like a little bit about what to do. And we said, okay, if we're gonna offload something, of course, we will not offload all of it. We said probably we'll offload maybe 10%, depending on the service, of course. So even if you offload only 10%, this would mean that you have to transmit at data rates of 32 megabits per second, going up to 450 megabits per second, which is huge. And actually, this is where it starts interesting. So actually, you say offloading, but offloading to what? And if you remember, I told you when we are not in an urban area, so actually, and you are in the highway, to what will you offload? And this is where it starts interesting. So we said aerial platforms can be helpful in this case. So if you can use drones, or if you can use HAPS or satellites, in this case, we can offload some of these tasks or some of this data to be processed elsewhere. And this is all the work that has been done here. So I just mentioned as a remark, this work has been led by one of my PhD students. I think she's attending today, and I will thank her for the tremendous work she did for this one. So actually, it starts very easy and very simple. So we said, okay, let's start see how can we offload some traffic from the cars, from the vehicles on a highway, and said, okay, non-terrestrial platforms is a very good option. They can be very helpful, and that's great. So we have different levels, of course, of non-terrestrial networks. We would have drones. So that one is very simple because now drones can be used anywhere. And you might have HAPS, for example. We might also have satellites, but in our work, we focused on HAPS and drones. And some specifics about these things is that drones, for example, they fly between 50 and 150 meters. They can maybe go to 200 meters in altitude. The problem, they have limited communication range. They don't have a lot of energy power. So their usage might be limited and temporary. You cannot use this as continuous platform. HAPS are a little bit better. So these HAPS are higher in altitude. They can go up to between 17 and 25 kilometers. They have a higher payload. So they might have large coverage. And also they might have more processing power, which is interesting. So what we did is that we started looking to their usage. First, we looked into a simple case. Let's say we deploy one drone, okay, on a highway. And then we want this drone to offload some traffic. So we make it simple. We said, okay, when we deploy this drone, we will not focus too much about how we will move it. We will just say, once you are launched at the altitude, let's say 100 meters, we just want you to target a segment of the highway, and then you just go this side and then come back this side and go this side and come back this side. And whenever you fly, try to offload, some tasks from the vehicles and satisfy them. And this is what we did at first. So this is what we did. We have this drone that have some data processing power, and it is receiving some data from vehicles, and then it processes them and, of course, give some feedback. So actually, you can think as a simple application as the vehicle is sending some images from the cameras, and you are just responding by if you identified obstacles on the road or things like that. And then you just run it like that. So what we did is that we have defined, of course, our communication model. Of course, air-to-ground communication model usually is dominated by line of sight. We also assume that we have no interference between uplink and downlink, so they are done in separate frequency bands. And then using the Shannon formula, we just define the data rates or achievable data rates for uplink and downlink. Then we consider that our drone has some processing power. Of course, if I have processing power to use to many tasks, then I might have queuing delay. So this is also accounted in a queue that goes into the processing power that we have in order to serve these tasks. So this has been also considered. And we have defined some parameters. For example, UAV has MM1 queue system to store incoming tasks, and then it has the memory cap limit Lmax, meaning that if I have more tasks than Lmax, I will just start dropping the new tasks. And then UAV computing power is defined by F, which is the number of cycles per second. So this is how we calculate or measure the power that we have for processing. Then we looked into the energy consumption. Of course, it's important because drone has very limited energy. And of course, energy consumption, you have some energy for flying. So when you fly the UAV, actually you consume a lot. And then you have task processing. When you process a task, also you will use some energy to do that. There is the third one that I did not show here, but which is the communication. I mean, once I'm giving back the feedback, so actually I will transmit something. But usually this transmission is 1% to 10% what is used for flying and processing. So usually you will just neglect it because it's like, less than 10%. So in this case, we just accounted for these two. And in parallel to that, you have to look to the delay. So why are we looking to the delay? Of course, because if I want to offload the task and I want to execute it, I have to make sure that I'm respecting the quality of service requirement that has been given to me. So in this case, we will calculate the delay between the vehicle, the CAV, and the drone. Here, the formula, it's not like the basic Shannon formula that you use to Y, because since both are moving, actually the channel is changing. So to have a better idea about the delay, you have to account for this change from, let's say, since time is discrete here, from one time slot to another. So that's why you have to make a summation over the data rate, achievable data rate for different time slots, and then multiply by the duration of one time slot. And this has to be higher than the size of the data that is being received from the vehicle. And then, of course, you might have queuing delay. We will also account for data processing delay. And the total delay will look as a summation of the three. So communication, queuing, and processing. This is the main delay expression here. So we formulate the problem. Here, the problem is to maximize task offloading success at the drone. So whenever I'm getting a task, I want to make sure that I'm satisfying the maximum number of the tasks I'm receiving. Of course, the constraint will be related to the quality of service. So task offloading delay is actually the tolerated time end-to-end, including communication and task offloading or processing. Of course, energy consumption also has to be respected based on the battery capacity that you have in the drone. And what we did here is that, since I told you we have our drone that once it's launched, it will just target a segment in the highway and just make a trajectory of come and go all the time, then we have to limit the locations of flying the drone. So in the optimization variables, we'll have the drone initial launch direction, and so the launch, not direction, launch location, and the flying direction. And of course, we have to account for successful tasks. So whenever I'm handling a task at the drone, I want to make sure that I'm respecting the quality of service. So the problem, I mean, if you look at it as symbols, it will look like this, but I think that's the idea behind it. I won't go through it again, but that's the idea behind this first problem. And then what we did is that we proposed different approaches. I mean, at first we looked into using genetic algorithms. So genetic algorithm task offloading. So we have defined our populations that includes initial location of the drone, initial flying direction, and the matrix of the successful offloading. And then we have defined the gene as the tasks to offload. We used a mating approach to combine the solutions. We defined the fitness function, which is related to the objective function that we have here, which is actually maximizing the success ratio. So the SMT is a binary variable that tells you that this task M has been satisfied or not. And then we will use, of course, mutations and elitism in the genetic algorithm to try to find the best solution possible. And then we considered another one, which is better because it transforms a part of the problem into a linear program. So actually, what we did is that we said, since we have many parameters to optimize, let's fix some of them and try to solve the other problems. So for example, if we fix the initial location and the targeted tasks that we want to satisfy, we can just decide on the initial direction of flying. It's either left or right. That's it. Then if we fix this left or right, and also what we want to aim as successful tasks, actually we can find the best location for the drone to launch it. And the third one, of course, the third sub-problem is that we fix the launch location and the first direction. And in this case, the problem becomes either we accept or reject tasks. So actually we accept them, meaning we guarantee the quality of service, or we reject them because we will be unable to satisfy it. And in this case, the problem becomes linear program, and we can, solve it with tools like CVX or AMPL. So this problem, which is called iterative exhaustive linear programming, why? Because theta has only two options. It's either left or right. So it's very easy to make these two problems with left and right. The locations, what we did also is that we make a discrete options on the segment. So if the segment, for example, is 1 kilometer in length, so what we did is that we say, okay, let's take initial locations going from 0 kilometers to 0 to 1,000 meters, and then we take a step of 10 meters. So we define the location of 10 meters. And by doing this, these parameters can be discrete. So it's easy to explore them all. So that's why the exhaustive part is here. But the problem of solving successful offloading or not, it's LP. So then you solve it. And this is what we did in the second approach. So for our simulations, we, of course, fixed some parameters for the task offloading. We fixed some parameters for the vehicles, for the drones, and of course for the communication, for the processing power, CPU frequency, etc., the battery capacity that we have, and of course in our scenario we have like a total mission time, which is actually 3,600 seconds that we have considered here. We have the bandwidth, so this is all about the communication part, and the road length. I mean, depending on what I'm going to show, it's going to be between 1 or 5 kilometers. And of course, we have considered some benchmarks for comparison, which are, for example, random launch. So we randomly select from where the drone is launched and the direction that it starts. Fixed launch, so it means that we fix the location and direction from the beginning, and we use it all the time. And best launch is to try to find the average best combination of the location and direction. And of course, in all these cases, we will solve the LP problem for task offloading. And this is what we got, for example, in terms of success task offloading ratio, for varying data size. So the data size is the data that is offloaded from the vehicle to the drone. So here you see we have these benchmarks, and then you can focus only on the green and the purple ones. These are the ELP and the genetic algorithm. So as you can see, they are very close. Both of them are very close, with maybe a slight advantage to ELP when the data size is bigger. But it's very, very, very limited. So actually here you see when the data size is small, we can get almost 100% of success ratio. But as much as increasing, our success ratio is decreasing, which is normal, because if you have bigger size, meaning more time for processing and more time for communication. So it plays against your target of respecting the quality of service requirement in terms of delay. And so this is more specific values about the execution time. So here what you see is the execution time. And you can see genetic algorithm, and this is expected, is the slowest one. It's very slow compared to the other ones. I mean, the nice thing is that the ELP is really fast. I mean, it's not as fast as the benchmark, but still, well, it's like 1 second, 1.3, 1.4, 3.7 seconds, which is actually fine. Let's say if you put it in a real setting. Then we looked into the impact when we have different road length. Okay, so going from 1 to 5 kilometers. And of course, we expect a degradation. But surprisingly, the degradation in the benchmarks is very pronounced here. But the degradation in our algorithms, genetic algorithm and ELP, are not so bad. I mean, they're almost, it's almost stable, actually. So it's really consistent. It's around 90% almost all the time, which is very good, meaning that these approaches are really able to get to something close to optimal or near optimal. So that was the first example where actually we explored that using one drone. So what we did in the next work is that we said, okay, now let's consider a more complex system. So now consider we have many drones, but also we have the HAPS, because we want to bring this additional edge computing power that comes with a higher payload for the HAPS. So here, slightly different. So the drones are not moving. We consider that they are hovering. So they're just hovering in some locations. And to make it simple, these locations are chosen such that coverage is not overlapping. So they might be close, but not overlapping. And we have enough, let's say, drones to cover our highway segment. And then we have a HAPS somewhere at 20 kilometers that will cover all of them. And of course, this is the system model, how it looks like. But then we have to redefine all the communication model, computing model, etc. So here, I'm not going too much into the details, but what I'm going to highlight is that the air-to-ground link between vehicles and drones is slightly different from drones to drones and drones to HAPS. So actually, the drones to vehicles, we would say most of the time, it's dominated by line of sight. But in reality, it doesn't mean it's 100% line of sight. It's not. It has also non-line of sight components. So in this case, we use the probabilistic channel model, where I actually have a probability of line of sight and probability of non-line of sight. But then the good news is that between drones and HAPS, this is fully line of sight, because it's all in the air. There are no obstacles there. And then you have these direct communications between them. I won't go into too much into detail, but here, if I recall very well, is that we have differences on the channels, the frequency bands actually that are used to communicate between drones and vehicles and between drones and HAPS and between drones and drones. So we don't want them to overlap, because we don't want, for example, communication between the drone and another drone or a HAPS would interfere with the communication coming from the vehicle. So this is also an important point that has been considered. So we assumed it's different bandwidths. And another complexity we have also considered is that rather than having one full task, actually the tasks are divided into subtasks, meaning that now to satisfy a task, actually here, for example, WM is one task. So actually it is composed by subtasks, WM1 to WMK. But there is a trick here, is that this set of subtasks, how are they linked together? So actually, simple case, it's linear. So to satisfy my task, I have to satisfy in this order subtask 1, 2, 3, and 4. It might be parallel, meaning that subtask 1, 2, 3 can be done in parallel, but then once we have the output here, it goes to task 4, and then it's done. Or it can be hybrid. So some of them can be parallel, some of them can be in series or linear like this. So this makes it a little bit tricky, because now you cannot, for example, satisfy subtask 4 if you don't get the outcome of these subtasks. And to make this even more complex, these subtasks can be offloaded to any node in our platforms, either to one drone, to many drones, or to some drones and the HAPS itself. So, which makes it a little bit more complex. In this case, we have to, so actually we define the matrix in order to say if a subtask would be assigned to a given HAPS or drone or not. So giving this, the delay analysis becomes more complex. So here, I've tried just to make it maybe to go simply about it, is that when we have subtasks, so now we have to uplink. So we have to send these subtasks to different drones. So to do that, we have already to know the dependency between them. So if subtask 2 has to wait for the execution to subtask 1, we have to account for it. So this is the dependency time. And then when we execute here, meaning that we process by our CPU, we process a subtask, then the result, I mean, this time will be accounted also in parallel with the dependency time in order to have the subtask end time. Of course, you have waiting time, because sometimes you have to wait to all the subtasks to be achieved in order to calculate your total, let's say, end-to-end offloading subtask. So I won't go through all of it, but it gives you, but to give you an idea is that the completion of one task is directed by the completion of the slowest subtask. And the slowest one usually is the one that depends on other ones before. That's how it is. So, so once we have our delay analysis achieved for our subtasks, we have to calculate the energy consumption. Again, here it's fragmented because now energy consumption is related to these subtasks. So actually it is related to where these subtasks are placed. If to achieve, if to process subtask number 2, I need to receive subtask number 1 from another drone or from the HAPS, I have to account for this additional transmission delay that comes from the other drone. Of course, if we are in the same drone, you can consider transmission between the output of subtask 1 to subtask 2 is 0 because they are in the same place. But once they are not in the same place, then you have to account this additional transmission. And if you set additional transmission, meaning you have to consume some energy to transmit, and this energy has to be accounted. So, I mean, this looks really complex, but to simplify, just focus on this. So we have some processing energy. This is processing the subtask itself. You have dependency energy. So in this case, it depends on if you need to transmit something from one to another, from one drone to another one, for example, to process the task. You have the consumed energy for feedback. So once you process all the tasks, you send the feedback. You remember in the previous work, we did not account for feedback from the drone to the vehicle. Here we do account for it. So here it's accounted for it. And then you have the consumed energy to relay data to drones not covering the related CIV. So again, in our system model, if I go back here, I told you that we are covered by drones here. But imagine I'm a vehicle here, and I started offloading my data to this one. And I just moved, and I went to the second part here, so under the coverage of a different drone. So actually, even if data processed here, and at the end, the feedback has to come here. So there is some additional transmission between these drones and to the vehicle in order to get the result. Because now you are very far from my coverage area, so I cannot give you my feedback. So I have to send to another drone and it give it to you. And this information or this process has been accounted also here. So this is from the UAV side. From the HAPS side, it's similar. Honestly, it's similar. So we have energy consumption if it's executing some subtasks. And of course, it accounts for the dependency, if there is some, and then the energy consumed to feedback results. So actually, this is important because here we consider that if a drone is not covered by any of, if a vehicle is not covered by any of the drone, meaning that he's in an area that is covered only by the HAPS, then it's the HAPS who will send you the feedback. So this is accounted also here. So now with all this information, we formulate a new problem. The problem is slightly different from the previous one. So here we want to maximize task offloading ratio, but also we want to preserve our system energy. So residual energy of the drones and the HAPS, we want to preserve as much of it. So in this case, we want to maximize success rate and also the residual energy. So we considered this as, you know, combined objectives. And of course, in terms of constraint, you always have the delay for executing the tasks. You have also now energy consumption at drones and at the HAPS. And of course, here you have energy consumption per drone or HAPS. So actually, when you see N here, when you say 0, it's HAPS, and 1 to N is the drones that you have. And of course, the total energy, we want it also to be less than the available energy of all platforms, the aerial platform that we are using. And then you have, of course, these constraints that are related to assignments. So we don't want to assign a subtask more than once to someone. And this is the binary nature. So in this case, you see that our optimization variables are task association, or actually subtask associations, which is the A between them. And the C here, actually, it's about the success ratio. So actually, you put it 1 if it's successful, or 0 if it's not successful offloading. So, and here to normalize actually these two objectives, we have used this formula. So actually, success ratio is normalized by the total number of subtasks that have tasks that have been generated in the system. And then the residual energy is normalized over the available total energy of the whole system. So again, we used again genetic algorithm here, so I won't go through it again. So we just adapted to our new problem, and we made some simulations. Here benchmarks are slightly different. So we consider the case where actually full local, meaning that only the vehicle is offloading all the tasks to its drone that is covering it, only the one that is covered. Random offloading, meaning we just offload the subtasks randomly between drones and HAPS. Capacity-based offloading is really to prioritize offloading subtasks with large data size to the nodes with the highest computation capacity. So we look to the computation capacity and say, okay, those ones goes here, the other ones goes here. And full HAPS offloading is really, we rely only on the HAPS for all offloading. And results are interesting. So actually you have these fully local is the worst one. So fully local, meaning that you're just using one drone that does not have a lot of energy. So at the end, it will not satisfy many tasks. Random, it's slightly better. Why? Because at some point randomly, you will put some tasks maybe in the HAPS, so the HAPS has enough power, processing power, so it will be fine. And then you have full HAPS. So full HAPS is good, and it's understandable again because HAPS has huge coverage, so it's covering everyone, and at the same time, it has a good payload for processing. But then you have capacity-based. So capacity-based meaning you look into the available processing capacity and then you assign. It's doing better, but still it's just 70% here. And then when you use genetic algorithm, so we solve the problem with genetic algorithm, we're getting something probably near optimal. So we get up to 80%. And here we say we have different profiles for traffic, low, medium, and high. And of course, as the traffic is higher, we will lose some service rate, but it is understandable. And in all cases, genetic algorithm is just providing the best performance. In this case, we looked also to energy consumption. So as you can see here, full HAPS is the worst because you're just consuming all the energy that you have in the HAPS, which is a lot. And then you see a genetic algorithm approach is not so bad. Actually, it's very close to the full local. So as if you are consuming as much energy as putting everything on one drone and still doing better, a lot better in terms of performance. So in low traffic, it looks really great. Medium high traffic, I mean, full HAPS still worst one. But genetic algorithm now, it is consuming more. But this is understandable. Why? Because it is compensating this higher performance by consuming more energy, meaning that it's trying to process more tasks. So this is the price to pay if you want to have more success ratio. And another case actually where we transpose service rate with energy consumption, where actually we consider the different models for the subtasks. You remember it's either linear, parallel, or hybrid. And just to tell you that in the previous one, it was all hybrid. And here we can see the profiles for the different approaches. So at the end, you can see the relation, for example, for the genetic algorithm that is giving the best performance in terms of service rate. And it's maybe the second best energy consuming after full local. Here, same thing, best performance in service rate, second best in energy consumption, same case in the third one. So meaning that actually the genetic algorithm approach here is still robust against using different subtask modeling. And to finish with this one, so the last work that have been done, is that we extended that work that I just showed you by saying, is there a way to even improve better the energy consumption for the drones and HAPS? And let's say here it's more on the drones. So you remember that I told you in this case, let me show again. When we had this system, I told you that these drones can relay subtasks to the other ones because you want to offload them here, not here. So these transmission, usually you will use active antennas to do it, right? So you will consume some power to do it. So what we said, can we do better? Rather than having this energy consumption in these communications between drones and drone and HAPS, can you use another technology that is passive or that is lower consuming? And this is what we did. We said reconfigurable intelligent surface is a great option because the reconfigurable intelligent surface can be passive and will not consume a lot of energy in relaying because we are considering the relaying case here. So what we did is that we leverage reconfigurable intelligent surface. So those of you who doesn't know what RIS is, so RIS actually is some sort of metamaterial surface that can allow you to control incident signals, to reflect them. So actually I'm saying reflection, but it's reflection not like a mirror, even beyond, in a controllable way. So you can control the angle that you will reflect your signal to. And this property, we have explored this before. So I'm showing here just like a small introduction because since 2021, we were one of the first groups that has proposed using these RIS on aerial platforms. And actually, we looked into the feasibility of using RIS on drones and using RIS also on HAPS and how it can work and if it's achievable. And of course, the answer is yes, it is possible. And now we see many people talking about RIS-equipped UAVs or RIS-equipped HAPS or even RIS-equipped satellites. So this is something that we initiated a few years back, and it had a lot of success. And actually, this is what we used here. This is what we considered. So we said, okay, now we have the same system, but our drones are now equipped with RIS. And actually, we identified 3 modes of operation for the drones. So they have offloading power, so processing power, so they are MAC servers. They can be RIS-based relay, so meaning reflecting signals with RIS, or they can use their active antenna for communication or for relaying. And why we kept the active antenna here? Simply because if I have subtasks distributed in different drones and they are dependent one of the other, I need to transmit the output of this subtask to the other one. And then don't have the choice then to use an active antenna in this case. So the RIS by itself, it cannot make active communication. I still need an active antenna to do that. So this is what we considered. For the rest of the assumptions, they are almost the same as the previous case. So I just skipped them. We considered subtasks, same case. Communication model here, the only change is that we have the RIS considered here. So once we have the RIS, meaning that now you have another optimization to do, is that to control the RIS. So now, depending on the incoming signal, you have to control the RIS to reflect your signal. And this is something that have been added to our problem. So again, we have these multi-modes. So RIS passive mode, where you have your HAPS relay subtask using its RIS between 2 nodes, or active modes, where actually it's an edge server or simply a relay using its antennas, or actually just initiating the communication by its active antenna. So again, same exercise, looking to communication delay, task computation delay. We considered waiting delay, of course, between the subtasks if they are in different nodes. And we calculated the subtask and time. And of course, we look into the total overall subtask offloading delay that we might have for our task. So here there is an example. Actually, it is a nice example where we show we have 4 subtasks that are assigned in different nodes. For example, 1 and 2 are in the HAPS, 3 is in UAV1, 4 is in UAV2. So actually, I need to process 1 and 2 before sending them to UAV1. and then process 3, and then send the output to UAV2, and then UAV2, after processing 4, will send the feedback to the vehicle. So this is the whole story about how we are doing task offloading or subtask offloading here. So we made all the calculations here for our delays, and then we formulated a similar problem at the previous one, so we kept the same objective. However, here, what is new is that we have more optimization parameters. So here we added 2 things, the phase shifting for the RIS, but also the transmit power that is used by the HAPS and UAVs when they use their active antennas. Because even when they have to use the active antenna to transmit signal, we want it to be the minimum. So we don't want to use much power. And this all relates to the quality of service, so the delay, task offloading delay, that we want to respect at the end. So I'll just skip this. So to solve this problem, since it's a multi-parameters problem, we have divided it into sub-problems. So actually, we used iterative optimization here, or alternative optimization, where we create sub-problems by fixing some parameters and solving the other ones at the same time. So we did this by fixing, for example, power allocation and phase shifting, and try to find task assignment or phase shifting, and to optimize it given the power allocation and the assignment. And then power control when we have the phase shifting and assignment, task assignment that are given. So, and then you alternate over the 3 of them. So this is how it's done. So I won't go more on details onto this, but this is how we did it. So it's alternating optimization by solving successively and iteratively these 3 sub-problems. So for the task assignment, once we fixed our phase shift and power, we linearized the constraints, we introduced some auxiliary variables, applied McCormick relaxation, and then our problem becomes a mixed integral linear program, a MILP, and we solve it using Gurubi. So this is, this is how you solve these type of problems. The second one for phase shifting.
Oh, well, sorry, we have 1 minute only left.
Yeah. Okay. So yeah. So I'm just explaining how we solve them, but I will skip it. So actually, we solve these sub problems. We put them together for our solution. So we use some benchmarks, of course, in our comparison and simulations. And our method, this is the blue line, actually, what we call JOPO. So actually, you see, again, in different types of traffic, we achieve the best success ratio, and energy consumption is not so bad. But the important one is this one, because we looked into energy per satisfied task. So how much energy you consume when you satisfy a task. And you can see it's very interesting that the JOPO one is low. It's like comparable to just offloading to drones, or of using the genetic algorithm of the previous work. So we are very close, and you can see in high traffic, we are even the best one. So meaning that you are really achieving a high success task offloading by consuming minimum energy. And that was the objective here. So to conclude, I'd like to say that we worked on, improving these types of task offloading to these aerial platforms for vehicular tasks. And you have seen that we use different approaches using the platforms and using the RIS in order to improve as much as possible these types of algorithms. So of course, this can be extended later for real-time deployment. And of course, in this case, someone would say, what can we use? And we can say, we can use some machine learning, reinforcement learning approaches to do that. So thank you, everyone. And if you have any questions, I'm over to it. Thank you.
Thank you so much. Very, very informative. Well, you're covering many, many topics, and actually I have tons of questions because it's very close to what I'm doing in one way or another, but I really appreciate it. And this kind of webinar is kind of an extension to another webinar we had in the center, which is about HAPS in general. Now you're providing another example of how HAPS can be utilized. Is there any question? I think there was a question in the chat talking about how about link failures when you were presenting initially? If you accounted for them.
Link failures. So actually, for now, in the channel model is very simple, meaning that when we put the drones, for example, in the first case, for example, when the drone is moving, we don't say link failure, but for us, if the distance is high, the data rate will be very low, and then it will impact the delay. So the delay will be high, and at some point it will exceed the quality of service. So in this case, it's a failure. So we don't say it directly, but it's linked to the channel model, how it's done. In the other cases, for the case where the drones are hovering and they cover an area, so this is very geometrically easier. So once you are no longer in this coverage area, you have a link failure.
Thank you. Any other question? I have a question about, I saw you accounted for the energy when you did the equations in the beginning, energy, like the battery life of the drone in the beginning. And did you like conclude the study as far as the energy consumption at the or energy profile on the drones after doing all these activities in communication with the cars?
So I will mention one remark. In the first work, we consider, like with the one drone, we considered the flying energy. But in the next ones, where we have UAVs and HAPS, we focused only on the energy for communication and offloading only. So the assumption is that we have part of the battery that is fixed or dedicated for flying. So we don't touch that. And then we have some power that is done for task offloading and communication. So we kept it like this. Why? Again, because if we included the flying energy, it dominates the whole thing. It dominates the whole component. And if it dominates, I mean, either you optimize or not your communication, you won't see a difference. I mean, you would see a difference, but it's like, 1%. It's very small, so it does not significantly can see the difference. So we said we keep it away. We consider it's dedicated. It's considered dedicated battery for flying, and then we have some dedicated power for offloading and communication.
Thank you. Any other question? As far as when you're doing the HAPS, I think maybe I have one more question about using the simulator. Did you find any good simulator to do the experimentation when it comes to HAPS, and or what was the simulation environment?
So here, the simulation environment, I think it was just Python. It was just all programmed, or MATLAB, if I'm not wrong, MATLAB or Python, one of them. But heads up, we are setting up a 5G test bed here, and we bought some drones. So the idea is really to do something. I mean, maybe not specifically these use cases, but actually the drones we bought, they have some strong Qualcomm processors. So we will be doing some edge computing on them. And probably with this test bed, we will get some interesting results for some examples of applications.
Okay, thank you. I promised last question, but this is my last question. Is burning question is about I don't know if you get managed to consider the environmental issues when it comes to communication between the cars and the drones and the HAPS together, because this can be impactful as far as communication. I mean, maybe this can, I'm sure it's an open area, but I don't know.
Yeah. So actually, for now, let's say channel models that are considering between drones and HAPS are just strong line of sight. There is nothing there. But the problem would be between the vehicles and the drones, depending on where you are. Of course, if you are in an urban area, you will say, okay, you have a problem here. You may have shadowing, you may have obstacles, and this you should account for. Then if you are on a highway, still it's open, right? So it's maybe if there is a tunnel, yes, you just lose communication. But if it's open highway, then you say, okay, it is dominated by line of sight, but of course there's probability of no line of sight because there are some trees on the sides. Sometimes the trucks will obstruct the communication link with the vehicle or something like that. So yeah, it's still open, but for now it's just models. So of course it's not realistic. Other thing maybe regarding what can be done is that, for example, in our case, we did not focus too much about which frequency band are you using, right? So, but if someone said, okay, I will check if I can do that with millimeter wave. And actually this is, and I will just go back to the first introduction when I talked about this autonomous, this autonomous driving. So actually, if you want to get these data rates, these huge, I mean, these high data rates, probably you will be looking for millimeter wave technology or something similar, because you want a large bandwidth to get this data rate. So yeah, for now, we didn't focus much, but of course, if you need to receive 450 megabits per second or 1 gigabits per second, you should use a more a higher data rate technology.
Thank you so much, Professor Jaafar. I really appreciate your time on behalf of Chicago State University, our Center for Information, Security Education Research, and also Carnations. And I really appreciate your time. Thank you so much. And it was very, very informative, and it was amazing. Thank you so much.
Thank you very much.
We'll connect with you soon.
And thank you for everyone for listening and for the questions. So if you have any other questions, feel free to reach out and we can talk about it. Thank you very much.
Thank you, sir, for your time. Thank you.